December 1944. Snow falls over the Ardennes forest. American soldiers gather around a massive steel beast that sits motionless in a Belgian clearing. Its tracks are frozen to the ground. Its engine is silent. Its crew has vanished into the winter fog. The tank bears the designation Tiger II, the most feared armored vehicle Nazi Germany ever built. 180 millimeters of frontal armor, an 88 millimeter gun capable of destroying any Allied tank at ranges exceeding 2,000 meters. Intelligence reports called it invincible. Field commanders warned that nothing in the Western arsenal could stop it. But as the first American ordnance specialists climbed onto that frozen hulk and began their examination, they noticed something unusual. Cracks. Thin fractures running along the armor plate near the turret ring. Internal spalling visible through a shell impact that never fully penetrated. The metal told a story that no German propaganda broadcast ever mentioned. Within weeks, samples from this tank and others like it would arrive at Aberdeen Proving Ground in Maryland. The tests that followed would rewrite everything the Allies believed about German armor superiority. If you want to discover the hidden truths of the Second World War, subscribe to this channel and tell us in the comments where you are watching from today. The Tiger II emerged from a specific crisis in German strategic thinking. By late 1942, Wehrmacht commanders on the Eastern Front reported disturbing encounters with a new Soviet heavy tank. The Kliment-Voroshilov series and the emerging IS designs demonstrated that the original Tiger, the Ausführung E, might soon face opponents it could not reliably defeat. The response from Berlin was predictable. Make it bigger, make it heavier, make it impossible to destroy. In August 1942, the Heereswaffenamt issued formal specifications to two competing firms. Porsche and Henschel would each design a chassis capable of mounting significantly thicker armor and the longer 88 millimeter Kampfwagenkanone 43 gun. The weapon itself was terrifying on paper, a muzzle velocity approaching 1,000 meters per second. Penetration values that exceeded anything fielded by the British or Americans. During practice firing, German crews achieved first-round hit probability of 100% at 1,000 meters, 95 to 97% at 1,500 meters, and 85 to 87% at 2,000 meters. Those numbers suggested a tank that could engage and destroy enemies before they even knew they were in danger. Krupp handled turret development while Porsche and Henschel focused on the hull. Porsche's design, designated VK4502P, featured an innovative petrol-electric drive system. But Hitler's weapons office found critical flaws in the design, and by November 1942, the order was canceled. However, 50 turrets had already been manufactured. These turrets, with their distinctive curved front plates and prominent commander's cupola bulge, were fitted to the first 50 Henschel hulls. This created the version often incorrectly called the Porsche turret, though both turret types were actually designed and built entirely by Krupp. The curved front plate presented an unexpected problem. Bending 100 millimeter armor plate into a smooth curve proved extremely difficult. The process induced tremendous internal stresses in the metal. Quality control inspectors noted that the curved sections were prone to cracking even before the vehicles left the factory. This was the first warning sign that something was fundamentally wrong with German armor production. The production turret, fitted to all Tiger IIs after the first 50, simplified the design considerably. The front plate was now a flat surface angled at 10 degrees from vertical, measuring 180 millimeters thick. The sides remained 80 millimeters, but were sloped at 20 degrees to accommodate the commander's position without the external bulge. The turret roof consisted of 3 separate 40 millimeter plates at varying angles. From pure geometry, the design appeared sound. The sloped front hull plate measured 150 millimeters thick at 50 degrees from vertical. Combined with the sloped turret face, this gave the Tiger II frontal protection that theoretically exceeded any tank on Earth. Allied intelligence officers calculated that no gun in current service could penetrate these surfaces at combat ranges. The alarm spread through headquarters from Normandy to the Ardennes. Commanders requested immediate updates on countermeasures. Staff planners prepared contingencies for enemy armor that simply could not be stopped. The first Tiger IIs entered combat on July 11, 1944, near Caen in Normandy. Schwer Panzerabteilung 503 deployed against British positions. The results seemed to confirm the worst Allied fears. British 6-pounder and 75mm rounds bounced harmlessly off the glacis plate at ranges under 500 yards. United States Intelligence Telegram number 1929, filed on July 15, noted with rare alarm that the armor appeared impenetrable to all weapons currently fielded. Field commanders anticipated catastrophic breakthroughs. A single Tiger II could anchor an entire defensive sector. A platoon of them might spearhead a counterattack that nothing could stop. But buried in the operational diaries and unit returns from that same week, a different story emerged. Schwer Panzerabteilung 503 recorded multiple non-combat losses within the first 72 hours. Overheating engines, final drive failures, fuel shortages that left tanks stranded before they ever reached the front. Of the 45 Tiger IIs committed to that initial action, nearly half were lost to mechanical breakdown rather than enemy fire. The Tiger II's weight approached 68 metric tons, making it the heaviest operational tank Germany ever fielded. The Maybach HL 230P30 engine produced 700 horsepower, giving a power-to-weight ratio of approximately 10 horsepower per ton. By comparison, the American Sherman achieved over 15 horsepower per ton. This difference manifested dramatically in mobility and mechanical stress. The Tiger II consumed roughly 2 American gallons of fuel per mile, or approximately 470 liters per 100 kilometers. During the Ardennes offensive, German logistics planners struggled to keep these fuel-hungry beasts supplied. Traffic jams on narrow forest roads delayed fuel convoys. Tanks ran dry while waiting. Crews abandoned vehicles that still had functioning guns simply because they could not move. The mechanics of war were rendering judgment independent of armor thickness or gun caliber. Inspector General of Panzer Troops Wolfgang Thomale addressed these problems in a briefing on November 4, 1944. He identified the new double-link track as particularly troublesome. The track design simplified production but created vulnerability to sideways stress when driving on uneven terrain. Only every other sprocket tooth engaged with the track, leading to rapid wear and potentially catastrophic final drive damage. Thomale noted that this engagement pattern caused sudden jerks in the final drive, which could not withstand the resulting shock loads. Henschel's chief designer, Erwin Otters, later wrote with evident frustration that the Tiger II went into production without adequate consideration of test results. The Wehrmacht was deploying a tank with known mechanical deficiencies because the strategic situation demanded armored vehicles, any armored vehicles, regardless of their operational readiness. By late autumn 1944, fewer than 120 of the approximately 489 Tiger IIs produced remained operational. The mathematics told a devastating story. German factories poured resources into building heavy tanks that spent more time in repair depots than on the battlefield. Each Tiger II represented the material equivalent of multiple Panzer IVs or Sturmgeschütz assault guns. The fuel and bridging footprint for a single Tiger II company equaled that of an entire Sherman battalion. Strategic planners faced an uncomfortable reality. The wonder weapon consumed resources at a rate Germany could not sustain while delivering combat results that rarely matched the propaganda images of invincible steel giants. Meanwhile, American and British intelligence organizations implemented systematic captured material exploitation. The Ordnance Technical Intelligence Section of the European Theater of Operations established procedures to capture, measure, and test enemy equipment. Firing tests would replace field rumors with data. Controlled experiments would determine actual resistance values and gun performance characteristics. The decision to centralize this effort meant that evidence would soon challenge long-standing assumptions about German armor superiority. Crates began arriving at various testing facilities. Each contained precisely cut sections of German tank plate, tagged with recovery coordinates, estimated thickness, and preliminary field observations. Torch crews marked cut lines in chalk across captured glacis plates. The cuts would yield sample slugs for laboratory analysis, micro-hardness measurements, macrographic examination, metallurgical evaluation of crystal structure and alloy composition. The Tiger II's reputation assumed homogeneous, consistently hard plate across all surfaces. The tests would soon reveal a very different reality. Soviet analysts at NII-48, the Armor Research Institute, had already documented disturbing trends in German armor quality. Their reports from captured Panthers and Tigers revealed that Germany had run into molybdenum shortages as early as late 1942. Molybdenum is a critical alloying element for armor steel. It provides hardenability, toughness, and resistance to heat. Without adequate molybdenum, armor plate becomes harder but more brittle. By June 1944, molybdenum had essentially vanished from German armor of all thicknesses. German metallurgists attempted to compensate by substituting vanadium and adjusting nickel content. Vanadium could maintain hardness, but could not replicate molybdenum's contribution to ductility. The result was armor that met surface hardness specifications but exhibited dramatically reduced impact resistance. This is important to understand. Stopping a bullet or shell is not just about hardness. Armor must absorb and distribute the tremendous shock energy of impact without cracking or spalling. If you want to keep learning, take a moment to subscribe and help us bring more stories like this to light. Aberdeen Proving Ground conducted systematic firing tests on captured Tiger II hulls as part of Project 5044 in July 1945. The results confirmed what metallurgical analysis had suggested. The armor tested was within specification for hardness. Carbon content actually exceeded the maximum specification, but Charpy impact values, the measure of how much energy a material can absorb before fracturing, were far below those required for armor plate of this thickness and hardness. The steel appeared clean and sound under microscopic examination. It contained sufficient alloy content to qualify as armor-class material. Yet, it performed poorly under impact testing. The conclusion was blunt. The plate investigated should be considered poor quality armor. The Tiger II's legendary protection was partly a mirage, created by raw thickness rather than properly engineered material. Soviet testing revealed similar findings from the Eastern Front. When panels from Tiger II glacis plates were subjected to ballistic testing, several showed dry fractures and crystalline traces rather than the fibrous fracture patterns associated with properly tempered armor. One upper sloped front plate fractured completely on only the second shot. Analysis showed abnormally high carbon content at 0.57%, lower quantities of chrome and nickel than standard, complete absence of molybdenum, and poor fracture characteristics. The causes traced directly to inadequate chemical composition combined with heat treatment failures. German industry simply could not maintain the material standards required to produce consistently reliable armor. In the second quarter of 1944, more than 30% of German armor batches failed their first quality control trials. 15% failed the second trials. About 8% failed even the third attempt. The biggest single cause of failure was spalling. Spalling occurs when the shock wave from a projectile impact causes fragments to break away from the inner surface of armor plate. Even when shells fail to penetrate, spalling can wound or eliminate crew members and damage internal components. Reports from both Eastern and Western fronts documented Tiger IIs rendered inoperable by hits that never actually pierced the armor. The welding was carefully executed, but significantly worse than on earlier German designs, including the Tiger I and Panther. Laboratory testing confirmed that the plates lacked molybdenum due to supply losses, with vanadium substitution inadequate to maintain proper impact resistance. The result was low malleability. When struck, even by non-penetrating hits, the armor often produced large amounts of internal spalling that damaged transmissions and other critical systems. A tank might survive the shell only to be immobilized by the fragments that shell created inside the fighting compartment. The substitution of vanadium for molybdenum was not inherently flawed. Vanadium is used in modern armor applications. The problem was that German metallurgists lacked time to properly develop heat treatment protocols for the new alloy compositions. Production pressure from the Nazi regime demanded output regardless of quality. Albert Speer's rationalization drive encouraged manufacturers to increase numbers at the expense of careful quality control. Allied strategic bombing forced the dispersal of German industry, with tank components subcontracted to inexperienced manufacturers who had never worked with armor steel. The increased reliance on forced and slave labor introduced additional quality problems. Workers who lacked training, motivation, or even adequate nutrition made mistakes. Sabotage was suspected in some cases, though difficult to prove. Multiple components broke down under field conditions that properly manufactured tanks should have survived. The Tiger II was not just poorly designed, it was poorly built. American ordnance specialists documented consistent final drive failures across Tiger II samples from different production batches, different factories, and different time periods. Early production units from 1944 exhibited the same failure modes as late production units from 1945. The consistency demonstrated systematic design inadequacy rather than random quality control lapses. The final drives simply could not handle the stress imposed by the tank's weight, combined with the limited torque capacity of the transmission. Technical Manual E-46, issued by British 21st Army Group Technical Intelligence, concluded that the German high-power transmission was unfit for sustained road marches. Tooth shear patterns indicated shock overload and insufficient lubrication. Heat-affected zones showed repeated thermal cycling beyond design limits. The Tiger II that looked so fearsome in propaganda photographs often could not complete a strategic movement without breaking down. Yet the Tiger II remained genuinely dangerous when it actually reached the battlefield in operational condition. The 88mm gun could eliminate any Allied tank at ranges where return fire had little chance of penetration. Lieutenant Colonel H.A. Shields of the American 66th Armored Regiment reported encountering Royal Tigers near Pottendorf that displayed excellent tactical mobility despite their size. The tanks negotiated soft ground without their tracks sinking as deeply as American Shermans. When properly maintained and adequately fueled, the Tiger II could perform. The problem was that it rarely enjoyed those conditions. Chronic fuel shortages, inadequate spare parts, overwhelmed maintenance units, and the relentless pressure of combat against numerically superior enemies meant that most Tiger IIs never demonstrated their theoretical capabilities. The Battle of the Bulge, Germany's last major offensive in the West, exposed these limitations dramatically. Hitler concentrated his remaining armor for a desperate thrust through the Ardennes, hoping to split Allied forces and capture Antwerp. Tiger IIs from several Schwer Panzerabteilungen participated. The narrow forest roads and winter conditions created nightmarish conditions for the heavy tanks. Traffic jams blocked fuel convoys, bridges collapsed under excessive weight. Mechanical breakdowns immobilized vehicles at critical moments. Tiger 222 was knocked out by American tank destroyers in Stavelot on December 19th. Others were abandoned when fuel ran out or final drives failed. German recovery crews attempted to retrieve damaged vehicles, sometimes operating in total darkness within meters of American positions. But as the offensive stalled and the threat of encirclement grew, crews increasingly chose to destroy their own tanks rather than let them fall into enemy hands intact. Total Tiger. 2 losses on the Western Front reached approximately 120 vehicles, 15 in Normandy, 15 in central France during August, 10 during Operation Market Garden, 15 during the Aschen-Hürtgen fighting, 30 during the Ardennes offensive, 35 in central Germany during April 1945. Many of these losses were not to enemy action, but to breakdown, fuel starvation, or deliberate destruction by retreating crews. The Tiger II achieved local tactical victories, but could not alter strategic reality. Germany lacked the industrial capacity to replace losses. Each destroyed Tiger II represented resources that could not be recovered. The wonder weapon consumed Germany's remaining strength while delivering diminishing returns. The contrast with American armor doctrine became increasingly apparent as testing continued. When ordnance specialists at Aberdeen fired the Tiger II's own 88mm gun at the frontal plate of an M4A3E2 jumbo Sherman, the results were unexpected. The shells bounced, not once but repeatedly. The feared 88, the gun that supposedly penetrated anything, failed against an American tank barely known outside its own divisions. The jumbo's frontal armor combined reasonable thickness with properly manufactured, high-quality steel. The gun mantlet and transmission housing created effective resistance without the excessive weight that plagued German designs. American metallurgy, casting techniques, and quality control had closed a gap that battlefield reports once suggested was unbridgeable. The Allies had not just matched German armor, in some critical respects, they had exceeded it. Lieutenant Harold Pfizer, a senior metallurgist at Aberdeen, summarized the findings in his official report. The Tiger II represents an engineering philosophy that prioritizes single engagement dominance over sustained operational capability. It is a dueling pistol in an era that requires repeating rifles. The metaphor captured the essential problem. Germany built tanks for individual combat excellence. The Allies built tanks for sustained warfare at industrial scale. The Sherman was easier to manufacture, transport, maintain, and replace. A destroyed Sherman could be replaced within days. A destroyed Tiger II was gone forever. The mathematics of attrition favored the nation that could produce and sustain larger numbers of adequate equipment over the nation that concentrated resources in fewer, theoretically superior but operationally fragile systems. The human cost of Germany's armor philosophy fell heavily on Tiger II crews. These men were not ordinary tankers. Heavy tank battalions received select personnel, often with extensive combat experience. They trained on vehicles that were supposed to make them invulnerable. Instead, they found themselves operating machines that broke down constantly, consumed fuel at impossible rates, and sometimes trapped them inside when transmission failures locked the drive sprockets. Drivers originally trained on lighter tanks were sent directly to operational units without adequate instruction on the Tiger II's idiosyncrasies. The combination of inadequate training and mechanical unreliability created conditions where even skilled crews could not extract the tank's potential performance. Many Tiger II crewmen never had the chance to engage the enemy. They struggled instead against their own vehicle's limitations. Soviet testing provided additional perspective on the Tiger II's actual combat effectiveness. At ranges of 400 meters, Soviet 122mm guns could penetrate the Tiger II's armor completely, passing through one side of the turret and exiting the other. The feared armor that supposedly stopped everything proved vulnerable to heavy Allied guns at realistic combat distances. The 152mm howitzers, commonly mounted on Soviet assault guns, could demolish a Tiger II without relying on precise penetration. The concussive force alone could crack the brittle armor, jam turret traverse mechanisms, or incapacitate crews through internal spalling. When combined with the Tiger II's mechanical unreliability, these vulnerabilities meant that the tank's survivability in extended combat was far lower than theoretical calculations suggested. The final accounting of Tiger II effectiveness must consider not just what the tank could do, but what it cost. Each Tiger II required approximately 300,000 Reichsmarks to produce, exclusive of the gun. The raw materials included critical alloys that Germany could not easily obtain. The specialized labor hours diverted skilled workers from other essential production. The fuel consumption during combat and transit devoured petroleum reserves that were already inadequate. The maintenance demands overwhelmed support units, struggling to keep simpler vehicles operational. All of this investment produced a vehicle that spent more time broken down than fighting. German industry might have produced 3 or 4 Panzer IVs for the cost of each Tiger II. Those additional medium tanks might have achieved greater aggregate combat effect than the handful of heavy tanks that actually reached the front in operational condition. By April 1945, the Tiger II's service was nearly complete. The surviving vehicles fought desperate rearguard actions in Hungary, Austria, and Czechoslovakia. Schwerpanzerabteilung 503, the unit that had first deployed the Tiger II in Normandy, retreated eastward as Soviet forces closed on Berlin. The battalion that once fielded 45 of Germany's most powerful tanks dwindled to a handful of operational vehicles and scattered crews. Some Tiger IIs were destroyed in combat against overwhelming odds. Others were abandoned when fuel or ammunition ran out. A few were captured intact, their crews having fled or surrendered. These captured vehicles became the subjects of the testing programs that revealed the truth behind the armor. The legacy of the Tiger II extends beyond its actual combat record. It became a symbol of German engineering ambition and the limits of that ambition when confronted with industrial reality. The tank that was supposed to dominate every battlefield instead demonstrated the dangers of over-engineering and resource misallocation. Prioritizing individual vehicle performance over producibility and reliability proved strategically disastrous. The Allies won not by building better tanks in the German sense, but by building enough tanks that worked reliably enough to sustain continuous operations. The Sherman was not individually superior to the Tiger II, but there were thousands of Shermans, and their crews could count on them to start each morning, travel to the battle, and still be running when the shooting stopped. Modern analysis has debated whether the Tiger II's armor quality issues were as severe as wartime tests suggested. Some historians note that the captured vehicles examined had often sustained previous battle damage, which might have weakened the armor independently of manufacturing defects. The practice of firing hundreds of rounds at test targets to determine precise resistance values far exceeded what any tank would experience in actual combat. A Tiger II might have survived many engagements without exhibiting the catastrophic failures documented in laboratory conditions. Yet the operational record supports the conclusion that something was fundamentally wrong. The breakdown rates were too consistent. The spalling damage was too widespread. The final drive failures were too predictable. Whatever the precise metallurgical explanation, the Tiger II simply did not perform as advertised. The examination of captured Tiger IIs validated an American approach to armored warfare that prioritized quality steel, intelligent geometry, and high-velocity penetrators over brute thickness. The 90mm gun, mounted on the M26 Pershing, could defeat Tiger II armor at practical combat ranges. The jumbo Sherman's front plate could resist the feared 88. American manufacturing delivered consistent material quality that German industry could no longer match. The gap between theoretical design and actual production had become Germany's fatal weakness. Engineers in Berlin could specify ideal armor compositions. Factories in the Ruhr could not reliably produce them. The Tiger II's armor was mostly a mirage because the steel inside that armor was not the steel the designers intended. The story of the Tiger II illuminates a broader truth about military technology. The most advanced design means nothing if it cannot be built, supplied, crewed, and maintained under combat conditions. Germany's heavy tank program consumed resources that might have sustained more numerous, more reliable armored forces. The Allies understood that warfare is fundamentally an industrial contest. The nation that manufactures more functional equipment will eventually prevail over the nation that manufactures fewer, more elaborate systems. This lesson echoed through subsequent military procurement debates. It continues to inform discussions about the balance between capability and quantity in modern armed forces. The Tiger II stands as a monument to engineering ambition and a warning about its limits. The soldiers who gathered around that frozen Tiger II in December 1944 could not know all of this. They saw only the massive hull, the long gun barrel, the thick armor plates. They felt the awe that German propaganda intended. But the ordnance specialists who cut into that armor, the metallurgists who analyzed those samples, the engineers who compiled their reports, saw something else. They saw cracks that should not have been there. They measured hardness without toughness. They documented a tank that Germany had built in desperation from compromised materials with insufficient quality control, hoping that intimidation would achieve what actual performance could not. The Mirage was dispelled. The armor that seemed impenetrable was revealed as brittle, prone to spalling, vulnerable to weapons that intelligent design and consistent manufacturing had created. The Tiger II's reputation rested on fear. The testing at Aberdeen and other facilities replaced fear with data, and the data said the king had no clothes, 180 millimeters of armor plate, 68 tons of steel and ambition, the most powerful gun Germany mounted in a tank turret. None of it mattered when the final drives failed, when the fuel ran out, when the crew abandoned the vehicle in a frozen Belgian forest because it simply would not move anymore. The Tiger II was not defeated by better tanks. It was defeated by mathematics, by logistics, by the industrial capacity that Germany could not match, and the manufacturing quality it could no longer maintain. American engineers examined the captured armor and admitted the truth. Much of what made the Tiger II fearsome existed only on paper, in specifications that factories could not meet, in alloy compositions that shortages would not allow. The armor was real steel, certainly, but it was not the steel it should have been, and in that gap between specification and reality, the myth of German armored invincibility finally died. Subscribe now to explore more untold stories from history's greatest conflicts. The wars of the 20th century still hold secrets waiting to be discovered. The Tiger II was only one chapter in a vast story of human courage, technological ambition, and the brutal calculus that decides the fate of nations. Every tank that rolled off an assembly line carried with it the hopes and fears of the people who built it and the soldiers who would fight inside it. Their stories deserve to be remembered, not as propaganda portrayed them, but as they actually were, complete with triumphs and failures, brilliant engineering and fatal compromises, courage in battle, and the mundane desperation of mechanical breakdown. That is the real history of armored warfare. That is the truth behind the Mirage.